Hi, this is Professor Cummings, and in this video, it's going to be more in the mechanical design area. And in this particular one, I want to go over cam design. Now, I'm not going to be able to do that in one video. I'm probably going to have this in maybe 2 or 3 videos because be able to give an actual example. But in this one, what I want to cover is some of the cam terminology and different types of configurations of cam so that you can kind of see what we're talking about here. So what you're looking at in this little picture, this little animation, is a small animation of a internal combustion engine. Now it blows up. You can see all the combustion going on in the combustion chamber, and then it blows up, and it actually gives you the guest of honor, the camshaft. Or in this particular case, you're looking down the camshaft at an actual cam lobe as it opens and closes a valve, for the exhaust and to go out into the manifold, as far as the intake manifold. So you can see the cam rotates, and as it rotates it touches the lobe touches the valve opens up, and it allows fresh air to be taken in. And you've got the complementary exhaust valve on the other side doing the exact same thing, and they're synchronized through either a gear train or a timing belt or a timing chain that allows these things to open up and close with a certain timing to it. And for most people, particularly people with a mechanical background, this is kind of intuitive, or kind of the basics of what a cam does. So this is essentially what a cam does. It kind of times things out and allows for some linear movement. Probably the easy example is that valve to move in a particular direction in a certain amount. But there's more to cams than just this. So this is just one example, but there's several of them out there. So this is just a very basic cam that I just brought up. And as you can see, all it is just, in this case, most likely say steel. It could be other types of material. The cam rotates around, and there's this lobe at the top, and you got this guy at the top riding on the cam, and that is known as a follower. Again, that's the whole purpose of a cam. It's a mechanical device that converts rotational motion into linear motion. Rotational motion, linear motion of the valve. But again, this is just a very basic example of a cam, and it comes in all sorts of different configurations. So you can see you've got this different type of design cam of a cam down here at the bottom. You've got the cam that's rotating around, opening and shutting these valves on this rocker, and then you got this device here, which is a totally different type of cam, but it is a cam nonetheless. And you still got the cam motion, which is that groove. It's again rotating, and you're causing a linear motion that goes parallel to the rotation of the axis. So in this case, it's going essentially perpendicular, and here you're traveling left to right, or horizontal. So again, there's all sorts of different configurations, and that's what we're going to go through in this video. So again, I mentioned the cam, over here at the bottom, and you've got this lobe sitting on top, and you've got a follower. A cam and the follower actually falls under the category of a type of linkage. If you look at our past video, we actually did a video on 4-bar linkages, and I just want you to see some of the similarities. So if you look at these two animations, again, I've just turned the cam on its side. You can see how it does have a lot in relationship to this 4-bar linkage. Now on this 4-bar linkage, you've got the input, or the short link, that's just rotating in a cranking motion. And then you've got you can call this link number 2. Link number 1 is the implied linkage, between the two base points. You've got linkage number 3, and then you've got a prismatic linkage driving it back and forth. So what you're seeing here is a rotational motion being converted into a linear motion based on the type of link. But cams are a little bit different, a little more sophisticated. And this is just showing how these are related. So in this case, your linkage 1 is still implied. Linkage 2 is the base, the round part of the cam, the bottom of the cam. Linkage 3, is actually helping with the extending or the horizontal motion, which would be what the purpose of that lobe is. And the prismatic lobe, the prismatic linkage, would be here down at the end, which helps create the linear motion. So if we were to try and draw a really good analogy between, you can see there is a relationship. And like I said, a cam is a little bit different than a 4-bar linkage in terms of its sophistication, or the nature of its kinematic pair. So if you remember from that video, the first video on linkages, the linkages and the 6 types of linkages are considered lower kinematic pairs, typically between 1 to 2 degrees of freedom. I think there was one with the actual 3 degrees of freedom. But with your higher pair, it means that you got a point or line contact from a curved or point contact between a moving body and a fixed body. So again, this is the perfect description of a cam. You've got a point or line of contact, you've got a round follower and a round cam, and that's what's causing your motion. So this is a higher pair, or a higher kinematic pair in terms of linkage if we use the same language. But other than that, it still is related to the 4-bar linkages. Now, one thing about cams that makes them valuable, that actually gives them value in terms of their mechanical abilities, is the basics in how they're designed. Now you can look at this again, a very basic cam, and you can watch how this follower is actually moving. All it does is have an up and down motion, and all that is encompassed by how this cam is actually has been designed. You notice there's an actual point when the follower stays put in this range, then it goes up, and then it actually travels down again from the peak. All that is designed into the cam and has some fairly sophisticated calculations, but you can actually capture all that motion in the cam. But before we start going into that, let's go into some of the terms and how this works. And probably the most important one, and the reason I named this slide Dwell in Cams and Followers, is the dwell. That is probably one of the more important motions of what the cam does. And the irony of it is it's actually a non-motion. When your cam and follower are in a dwell, you're literally not moving. But to give it a more technical definition, dwell is the cessation of the follower motion, meaning the follower motion has stopped, while the input motion, how much that cam is rotating is the input, continues for a portion of the cam. So in other words, it's the ability to stop the follower from moving without the entire system stopping to move. So the follower stays put, and that is called a dwell, even though the camshaft or the cam itself is still in rotation, and that's dwelling. And again, like you can see, it actually still goes through rising and falling, and it could potentially have 2 dwells in it. But this is what allows you to control the motion, to actually be really specific with how this thing is going to move. And this is just a diagram of the displacement of the follower, how much this follower is rising. In this case, it's rising to a point of h, of a height of h. Going through a rise motion, then it goes through a dwell where it actually just stays at that height of h. In other words, the follower is no longer moving, and then you design it so it actually falls and hits another dwell where it stays put. And you can actually calculate or describe the motion of this cam through how much that cam has rotated, going from 0 degrees, or a portion that you designated the 0 degree point, all the way to its full rotation of 360 degrees. Now, again, I wanted to move away from some of the simplistic cams, and I just like this animation here of showing the different ways that cams can be designed and the very sophisticated motion that you can gain from just different types of how cams are designed. If you look at this animation, you can see that there are several very unusual rises and falls designed into these cams, and also different ways that the dwells are used. And if you use these things correctly, you can come up with a whole series of motions just with a cam system. So that is part of the beauty of cams. Now, since we can kind of understand how cams work, the basics of how they work, you got to see how they're actually classified. Now, there are 4 basic classifications of cam, and they all have a certain amount of value and certain drawbacks to them. So the first type of cam, and the most simple, is a knife edge, and that is as close as how you can actually describe it. The follower itself actually comes to a very sharp point, and it rides along the cam. So as the cam moves, it actually rides on this knife edge, causing it to go up and down. Now, one of the downsides of this is that you have a lot of wear due to this small area of contact. So it's a lot of pressure and a lot of wear, and it tends to have a slightly more abrupt style of motion. Another one is a flat face cam. Now, this is the thrust face, is that the bearing exerted is less than compared to other followers. So again, so the thrust face, the force going up is a little less compared to other followers, and you get a little less wear. And your motion is a little, the abruptness or the gentleness of the rise and fall of the follower actually changes. Then you've got something called a roller, which is what we saw in a few of the other animations, where it's actually a wheel riding over the cam. It has a very, much less of a wear rate, so it's not as much wear between the two, because of that motion of contact, so it just takes away some of the friction. So you can think of it almost like you're riding on a bearing, or it serves kind of the same purpose of the bearing itself. And then you've got a curved surface. Sometimes it's called a shoe or a spherical surface. So you're riding on a round surface, but it doesn't roll. So it's got a curved surface, so there's really just a point or a line of contact between the two different, between the cam and the follower. So those are 4 classifications of the cam and the follower itself, or the follower. Another thing to look at is how the cam is designed. Now, what we saw before were just cams and lobes, but there is something called a cylindrical cam, and we saw one animation of this, where this is literally a cylinder, and you've got a groove that allows for the cam, the follower, to travel within, as opposed to riding over a lobe and a base circle. So again, this is just a follower, and what you gain from that is a very specific type of linear motion. Goes parallel to the axis of rotation of the cam itself. So the follower oscillates parallel to the cam, and you can get any number of different types of strange designs in this type of cylindrical cam, but you're ultimately controlling the linear motion of the rod as it travels along. Another type of cam is called the globoidal cam, which is similar to a cylindrical cam, except for it has a profile, either a convex profile or a concave profile, which gives you an added degree of freedom to how the cam moves. Again, you can see this one is on a pivoting, a different type of linkage, so pivoting rotation for the follower. Still follows the groove, the same as the cylindrical cam, but again, it also follows this outer profile of the cam itself. That's the globoidal cam. And then there is something known as the wedge cam, which again is very, very basic, and your follower is perpendicular to the cam itself. So the cam here is actually this wedge, and this is a very simplistic wedge. I mean, it literally is just an incline that moves from left to right, allowing the cam to go up and down. All right, so you're perpendicular to the travel of the cam. And again, this is just one simplistic one that can actually give you different types of configurations. It doesn't have to be a rigid incline. It can actually be a gentle slope, but still follows the same idea as the wedge cam. The cam is actually traveling back and forth, and the pattern within this cam is giving you that up and down motion. And you can see, I like this particular animation because you can see the travel, the height of that follower, can take on any number of paths. So, here you've got a larger hump, goes to a max height, and then it comes down to a dip, and then rises slightly again, and then it goes all the way down to another drop. So in this, and this can be any number of types of things as a wedge cam. Now, some more in terminology. What we've looked at up to now has been known as radial followers. So you can see that the center line of the follower actually is in line with the center line of the cam's rotation. but there is a different type. One is called the offset follower. Here your center line of the follower is offset from the rotation. So what this does is it actually changes a bit of how that rise and fall takes place. Since the height, max height of the cam changes relative to where this follower is in relationship to that axis of rotation. So again, you can see this would actually have a slightly different profile in terms of its rise, fall, and its dwell. One of the benefits of that is it reduces the wear of the follower as well as the thrust force. That's one reason why someone would want a offset follower. Now, just going into some real basic terminologies, this is, you got a cam, and I like this picture at the bottom, which is kind of showing the similarities, some of the terms with gearing. You've got number one, the base circle. So again, the base circle is just the round portion and the theoretical circle that the cam is rotating about. So that's what determines the overall size of the cam. Then there's the trace point, which is the follower, the center of the follower as it's going to travel around the cam. And the pitch curve, which is the path of the trace point is going to follow. You got the prime circle, which is just a concentric to the base circle. Here's the base circle, and going around that is the pitch circle, tangent to the pitch curve. There's the prime circle, and then you got the pressure angle. You also have a pressure angle when you have an involute in the gears. So it's the angle between the direction of the follower movement and the normal to the pitch curve at any point is called the pressure angle. In this case, the pressure angle is still referred to as alpha. And then last is the actual pitch point. And this corresponds to the point of maximum pressure angle and a circle drawn with its with its center at the cam center. To pass through the pitch point is known as the pitch circle. So again, this is Professor Cummings. Thanks for watching. I just wanted to go through this video, give you some terminology as far as how cams are designed. So now you got a list of words to help you describe cam and cam movement and different cam configuration. In future videos, I'll go through some of the calculations to help understand cam motion, and then finally some examples. But thanks for watching, and see you in the next video.